Hello, my name is Huidong Hu. I am from the National Space Science Center, Chinese Academy of Sciences. The title of the talk is Limb Observations of Global Solar Coronal UV Wavefronts, the inclination, kinematics, coupling with the expanding CMEs, and the connection with the CME-driven shocks. I will explain them respectively later. Now we come to the introduction. An UV wave is a coronal disturbance caused by solar eruptions observed in extreme ultraviolet bands. After the discovery, it was interpreted with MHD waves or non-wave models, such as stretching magnetic fields caused by the expansion of CMEs or successive reconnection between the expanding CME and the background magnetic fields, or current shields surrounding the expanding flux loops. Currently, a combined interpretation is more favored, which consists of wave and non-wave components, where the non-wave component is the expanding CMEs, which drives the wave component. If an UV wave is associated with a shock, previous studies have suggested that it is related to the acceleration and the distribution of solar energetical particles. Here come our motivations. Previous studies have suggested that an UV wave has a 3D structure in a low corona, and the wavefront is forward inclined. The inclination is frequently explained by the increase of Arfan speed or faster magnetosonic speed in a low corona. In this study, we want to check if this is true for all events. The inclination also affects the estimate of actual speed of an UV wave. As shown in this schematic figure, the actual speed is perpendicular to the wavefront, which equals to the apparent speed multiplied by the sine of the inclination angle. This shows that if the UV wave is propagating on the solar disk, the inclination will affect the estimate of the actual wave speed. Additionally, the projection effect will also affect the determination of the altitude corresponding to the measured speed. To avoid the projection effect, investigation of limb events is required. The decoupling of the wave and the non-wave components of an UV wave has been frequently observed. In this study, we would like to check if there is no decoupling in some UV waves. An UV wave in the early stage is the footprint of the associated CME-driven shock. CME-driven shock can propagate to the other side of the Sun opposite the eruption site. For a special case, on 2017 September 10, in the contribution of the transmission of two large-scale polar coronal holes, the UV wave also traveled to the opposite side. During the whole propagation, the UV wave is continually connected with the white light CME-driven shock. In this study, we will look up the connection when a CME-driven shock has propagated to the opposite side of the Sun while the associated UV wave does not. Based on the motivation, we set the criteria of event selection. To avoid the projection effect, all the events should be on the solar limb, and to make sure that CME-driven shock has propagated to the other side of the Sun, all the events should be recorded as halos. To reduce uncertainty of averaged wave speed, all the events should have traveled a considerable large distance on the limb. With these criteria, 6 UV wave events on the solar limb have been selected. Now we come to the results. The first one is the inclination of the wavefront. In 5 of the 6 events, clear wavefront inclination is observed in the early stage of the propagation. The inclination angle is from 60 to 70 degrees. In the early stage, the wave is still coupled with the CME. We suggest that the inclination is attributed to the local geometry of the expanding CME loops. In 2 cases, the UV wave has been transmitted by large-scale coronal holes. After the transmission, the inclination angle has reduced to about 38 degrees. This means that the actual wave speed is about 40% lower than the apparent speed. After the transmission, the UV wave should travel freely and the forward inclination may be explained with the increase of alpha speed in the low corona. These four plots show the separation of time-distance profiles of the wavefront at different altitudes because of the wavefront inclination. The next result is about the kinematics. By comparison, measured speed with the MHD output from the predictive science incorporated, we see that 5 of the 6 UV waves are shocks. Besides this, we find that in 3 cases, the wave speed is locally elevated only below 1.1 solar radii. By investigating the magnetic configuration with a PFSS model, it is suggested that the local elevation is associated with local loops in the low corona on the limb. The difference of wave speeds at lower and higher altitudes indicates that the wavefront is distorted in the speed elevation region. This is the third result. The two figures show the LASCO C2 running difference images, where the sign line indicates the position angle when the UV wave disappeared, and the thick pink dashed line indicates the position angle of the CME boundary at the same time. We can see that the difference between the two position angles are almost zero. This suggests that the UV wave is continuously driven by the CME until it vanished. It means that the wave does not decouple from the CME driver for the two events. The 4 panels are also the LASCO C2 images, where the pink line indicates the angular position of the CME-driven shock on the other side, and the sign line indicates the position where the UV wave faded out. We can see that the CME-driven shock is at least 70 degrees ahead of the UV wave front. This suggests that after traveling to the opposite side, the CME-driven shock should have disconnected from the low corona UV wave. This is possibly because that in the low corona, the inclination angle of the CME-driven shock is nearly zero, and the shock eventually crashes on the solar surface and dissipates. Here are our conclusions. For 5 of the 6 events, the inclination of the primary UV wavefronts is attributed to the local geometry of the forward inclined loops of the expanding CME in the low corona. In 2 events, the inclination of the transmit UV wavefronts can be explained by the fast magnetosonic speed increasing with the altitude in the low corona. The large inclination of the transmit wavefront can significantly affect the estimate of the actual speed with about 40%. The wavefront speed is elevated by local loop systems only at a lower altitude below 1.1 solar radii in 3 of the 6 events, which results in distortion of the wavefront in the low corona. The UV wavefront can be coupled with and driven by the CME during the entire propagation, which is observed in 2 of the 6 events. In 4 of the 6 events, after the CME-driven shock has propagated to the opposite side of the Sun, the shock is no longer connected with the UV wavefront and dissipates in the low corona. More details are available in this article. Supporting movies are also available on YouTube. Any questions are welcome. You could find the paper with the paper number and leave messages on the AGU24 platform. I'll stop here. Thank you for your time.